the practice exam is going to be pretty similar to what you guys can expect on the final exam. Okay, types of problems, even format. Okay, there's really not going to be any multiple choice or fill in the blank, stuff like that. It's going to be problem solving. So if you guys went over the final or the practice final and you feel pretty good about it, then you should be pretty rock solid for the exam on Thursday. And like with the midterm, what I'll do is I will give you guys the allotted time, and you guys can start that whenever you want on Thursday. So it doesn't have to be from 1 to 3. It can be as early as 4 o'clock in the morning if you want to. Okay. So what I wanted to do in this review session is just simply go over the problems on that practice exam. Now, hopefully those problems look pretty familiar because they're mostly problems that we went over in the lecture. And I did that on purpose because I wanted you, if you were stuck on something, to be able to look back at your notes or go check out the videos that are recorded to see us go through those problems. And also, it gives you that problem a second time around. So hopefully they looked familiar. Hopefully they weren't too terrible. And let's dig into it and go over it now. Okay. So the first question is simply writing reaction quotients. And hopefully we all got this down pretty well because, if you can't write a reaction quotient, you're going to be in trouble for the rest of the problems downstream, right? So remember that your reaction, some little kid stole my eraser again. Okay. I will be right back. I got to go find an eraser. Sorry about that. Okay, I'm back. Kids these days, always making off with the erasers. All right, so what is a reaction quotient? It's just products over reactants taken to the power of their coefficient, right? So we would say, let me make it big. We would say that QC is what? It's going to be oxygen, or should I say that is ozone to the second power over oxygen to the third power for A. Right? What would B be? Anybody?
Ammonia squared over N2 times H2 cubed.
Squared over, what'd you say, N2?
Yeah.
Times
H2 cubed.
Yeah. Okay.
So if it doesn't specify pressure or concentration, we just do the little concentration brackets, right?
Yeah.
Okay.
Exactly. And then the last one, that would be pull it up here. Okay. Would be NO2 raised to the fourth times H2O sixth ammonia to fourth and oxygen seventh. Okay. Again, hopefully that's pretty straightforward.
I had a question about including water, because I think for the equilibrium, we don't include water, right?
Correct.
Okay, but for the reaction quotient, you do put water in? Okay.
Yep, good question. Now, you're not really going to have a problem, I don't think, where I doubt you'll have a problem where you have water in there. But yeah, when we're doing our particularly acid base equilibrium, the water doesn't count. Okay.
Is that true for other equilibrium constants?
Well, not necessarily, because if we're looking at the equilibrium between phases, remember we first start off in saying that, you know, it can go, if it's going back and forth between a gas and a liquid, then that would be water. But yes, I think in general, there's not going to be reactions with water that you'll need to take into consideration for equilibrium. Okay, maybe for a reaction quotient, but not for equilibrium. Whether it's an acid-base equilibrium or just a gas equilibrium. All right. So the next problem was, okay, so we're adding 0.1 mole of NO2 to a 1.0 liter flask at 25C. Keep dropping my marker. And the concentration changes so that the equilibrium is blah, blah, blah. Gives us the reaction, and it says, what is the value of the reaction quotient before any reaction occurs? So all we're doing is writing out what we're given, okay? How do we find, we're just given the concentration of nitrogen dioxide, right? Not dinitrogen tetroxide. So the initial concentration is 0.10 moles per 1 liter, which is 0.10 divided by 1, which is just 0.1, right? So that is in our equation, that is the reactant. So it's going to be 0.10 squared. And then the concentration of our dinitrogen tetroxide is 0 because this is initial, right? So 0 divided by something is 0. So that is our first step, right? That is the value of the reaction quotient before the reaction occurs. And then what is the value of the equilibrium constant for the reaction? Well, now what we're given is that nitrogen dioxide is 0.016 molar and dinitrogen tetroxide is 0.042 molar. Now we can just change those values to get our equilibrium. So nitrogen, dinitrogen tetroxide is 0.042. There's no coefficient, that's just the 1 power, and then 0.016 squared because of the 2 coefficient for nitrogen dioxide. And did anybody do that? What do you get when you divide this by this squared?
Uh, 164.06.
Oh. Okay. So that's our answer. Okay. So we're starting off just like we do in lecture, right? Starting off basic, and then we ramp it up as we go along. So number 3, below are the starting concentrations of reactants and products for 3 experiments involving the following reaction. And they give us the equilibrium concentration, or the equilibrium constant. And then they say, determine which direction it goes in all 3. So what do we do for this? We set up our reaction quotients for each experiment, just like we did in the first 2 problems, right? So let's see, experiment. Well, let's do our reaction quotient first. We would say Q is equal to H2 and CO2 over CO and H2O. And again, we're not doing an ice table or anything like that, so we still want to have our H2O in our equilibrium quotient. Sorry. So let's just plug in the values for experiment 1. So CO, oh, sorry, I think I wrote it as CO2, didn't I? Oh, no, it is CO2. Sorry. CO, though, down here is 0.0203. 0.0203. And water is the same. 0.0203. And carbon dioxide is 0.0040. And same thing here. 0.0040. All right, who did this? Essentially 0.0040 squared divided by 0.0203 squared.
$0.039.
0.039. Okay. Now, what did they say was the case C? They said the case C is 0.64. So in this case, K is greater than Q. They're asking which direction is it going to go? Well, remember, we talked about that. Let's see where, right here, predicting the direction of a reaction. And we said when K is greater than Q, the reaction will proceed forward or to the right side or to the product side. If Q is less, I'm sorry, if K is less than Q, then the reaction will proceed in the reverse direction toward the reactants. So in this case, K is greater than Q, so it's going to proceed toward the products. Right? Determine which direction. So you could say forward or products. Because if it was the other way, it'd be reverse or reactants. Or you could do left, reverse, reactants, right, forward, products, whatever you want to do. Okay.
Is like product favored the right way to say that?
Yes, you could say product favored, meaning it's going to go to the products until these equal each other. If it's the other way, it's going to go toward the reactants, reactant favored, until they equal each other. And that's at equilibrium, right? When K equals Q, it's at equilibrium. And it's going to go either left or right until that happens. So let's look at, I'm not going to do, I think I need to do all three unless you want me to. But let's do experiment 2. Now we have 0, 0, we have 0 0.011, 0 0.0011, 0 0.037, and 0 0.046. Okay. What do we get for that?
I got 140.66.
Okay. So now Q is greater than 0.64, right? And so it's going to be reactant favored, or it's going to go in reverse order, or it's going to go to the left. Let's do the last one. Why not? Okay. So the last one we have 0.0094 and 0.0025 and 0015 and 0076. What do we get there? Anybody?
.485, I think.
Okay. So again, Q is less than K, right? Because K is 0.64. So it's going to go toward products. Now, what if you got 0.64? What would you say? You'd say, well, they're equal. And you'd say they're at equilibrium. Okay, you got a problem like that. All righty. Nitrogen monoxide, one of several pollutants in exhaust, is oxidized to nitrogen dioxide in the atmosphere. It gives us the equation. And it says, if Kp is 2.2 times 10 to the 12th at 25 C, find Kc. Okay, for this, you need to remember Let me find it. The relationship of Kc and Kp. Right here. Kp equals Kc over times RT to the difference in moles of the reaction. All right. So let's write that reaction out. We have nitrogen monoxide plus O2, right? Goes to nitrogen dioxide, 2, right? Is that what it was? Methinks. Yeah. Okay. And if we know that Kp equals Kc times RT to the delta N, we can rearrange this because we have Kp. Wait a minute, hold on. What did they say our Kp was? Like 2.2 times 10 to the 12. Where'd you go? Uh-oh. Not that. That's wrong. There we go. Yeah, 2.2 times 10 to the 12. So we can write 2.2 times 10 to the 12 equals, well, let's write it on this side. 2.2 times 10 to the 12 equals K. What was that again? Sorry. That's Kp. They want us to find Kc. Let's try it 3rd time's a charm. Kp, try to find Kc. So we can say that that's 2.2 times 10 to the 12 over RT delta N. Okay. So what do we fill in for RT delta N? We got to know which gas law constant. Because this is pressure, we want to use the 0.08206 liters times atmosphere per mole times K. And then temperature, it said it was 25 degrees Celsius, but we got to put that in Kelvin, right? So then this becomes 0.08206 atmosphere liter mole K times 298.15 K. And what's the power? What's the delta N? Right here.
The change in the number of moles?
Yeah, exactly. Products minus reactants. So, anybody know what that number would be?
-1.
Yes, because our products, we have 2 coefficient. Our reactants, we have 2. And then even though there's nothing here, if there's nothing there, that's a 1. So that's 3. So 2 minus 3 is a -1. Okay, so all of that is risen to the power of -1. What happens when we calculate that out? -1 came from, let me just, oops, sorry. Let me share my screen. So -1 is the delta n. And where do we have that in here? Slide deck. No, I guess not. We use this equation. Raised to the power of delta n is just the difference between the coefficients of the products and the coefficients of the reactants. And so since the product coefficient was 2 and the reactants were 2 and 1, it's going to be 2 minus 3 equals a -1. Okay? Okay, so, okay, good. 5.38 times 10 to the 10. No, I'm sorry, the answer below me. Okay, below that, 10 to the, it's a hybrid. Okay, 10 to the 13. 5.38 times 10 to the 13. And it looks like you guys all agree on that. Okay, great. All righty. So the next problem gives us this. Iodine and chlorine yields 2 iodochlorine or iodochloride molecules. They give us the Kp. They give us the Kp, and they say that a reaction mixture contains the following concentrations. Is the reaction mixture at equilibrium? And if not, which way will it proceed? Okay, so these these atmospheric pressures, the partial pressures that they're giving us, are what we can use in our reaction quotient. And so all we have to do is solve for Q, P, by plugging those in. And then if it's greater or less than or equal to, that will give us our answer. So we can say that QP is equal to, okay, so iodochloride pressure is 0.355 atmospheres. And in this case, the brackets aren't denoting concentration. So we could make them more like parentheses if that's less confusing. Over, oh, and that is squared. And then I2, 0.114 atmospheres and 0.102 atmospheres. What do we get when we do that?
10.84.
Okay. Now they said that the Kp is 81.9. So if that's the case, then K is greater than Q. And so which way is it going to go?
To the right, product favored.
Exactly. Forward, right, product favored. You know what? I don't know if we actually went over any KSP. Did we go over the solubility? Do we go over solubility equilibrium?
No.
Okay. Well, let's skip that one, and if we have time, we'll come back to it because, but there won't be any KSP on the exam. I realize that now that I think about it. I don't think we covered that. But maybe you guys worked on it. This I know we covered. Free energies of formation to calculate equilibrium constant for a reaction at 298 K. All right, so what do we have here? We have the delta G values, or the free energy values. And then we also need to remember that relationship right here, right? That the free energy of the reaction is equal to a negative gas law temperature natural log of K. And in this case, we use a different R, or a different gas law constant, because we're not dealing with pressures. So we don't want to have atmospheres in there. We want to use the 8.3145 joules per mole K. All right. So let's go back to the problem and let's see what they give us. And then let's write down that equation. So delta G of the reaction equals a negative RT natural log of K. And the R is 8.1345 joules per mole. Okay. Oops. Okay. Got that. We have to get our free energy of reaction. Remember what that is? Again, products minus reactants. So for nitrogen dioxide, they're saying it's 51.3 kilojoules. And that'll be minus 99.8 kilojoules. Now, am I missing anything?
Yeah, multiply the 51.3 times 2.
Yeah, because, well, it's not on here, because of the reaction, right? So we have a 2 here. And so we could say that the free energy of the reaction, oops, let me stop sharing here so you can see the board better. The free energy of the reaction is equal to the sum of, what's up? Yeah, that's fine. The sum of the products times their respective coefficients minus the sum of the reactants times their respective coefficient. So that's where we get the 2 times 51.3, because in that reaction, the coefficient is 2. Okay. So what's 2 times 51.3 minus 99.8?
2.8.
Okay. 2.8 kilojoules.
So
Now-
just to clarify, are we trying to solve for the K? Is that right?
Let me just see here. Use free energies to calculate the equilibrium constant. So yes, we're solving K. We should have everything we need now in this reaction except for K. Okay. Okay. So we have this. Now, remember, our units for R are joules per mole. So if we rearrange this equation to get K by itself, we could say that the natural log of K is equal to 2.8 times 10 to the 3 joules, right? I took that 2.8 and I just converted it from kilojoules to joules. Divided by what? .3145. Oh, this would be negative, right? We got this negative sign here. Joules per mole K. And then there's a 298 K, that's what they said. What do we get for that?
Negative 1.13.
Okay. Now, but that's the natural log of K, right? So if we want to get just K, we take the natural log and we take e to the power of that natural log of K, right? So, yeah, you can see K would be e to the negative 1.13 or 10, right? 10 to the power of that number. And what's that?
0.323.
And that's our answer. Okay. Any questions on that? Now, do you need to memorize this equation? No. You need to remember the Kp is equal to Kc RT to the delta N? No. You just need to know when to use them. Okay. So if you got a problem that's giving you free energy values or delta G values, know to do this, to get this, and then plug in what you're given here. Who knows? Maybe it'll give you the K and ask for what temperature is that at. But chances are the K you're solving for. Carbon monoxide plus hydrogen yields methanol. The reaction at 780 degrees Celsius initially contains these concentrations, and then at equilibrium, the concentration of CO is found to be at 0.15. What is the value of the equilibrium constant? So, what do we do? What do we do when we're given initial concentrations and maybe a equilibrium concentration and asked to find the constant?
Ice table.
Okay, I was going to play my song. Ice Ice Baby. That's what we do. Okay. So let's look at this. We have carbon monoxide, hydrogen gas, yields methanol. They say that initially carbon monoxide is 0.500. Hydrogen is 1.0. And then at equilibrium, CO is 0.15. How do we fill in the rest? Say this is 0. Well, this one is easy, right? Because we have an initial and a final, essentially. So all we need to know is the difference, okay? And that's what, 0.035. So it's going down, right? It decreased. We know that we know that this is negative because it went from 0.5 to 0.15, which is less. So this is negative. This is negative. Now I got to make sure I got my reaction correct.
I think it's
2.
2.
It's 2H2, right? So it's going to be 2 times 0.35. So negative 0.70. And then that's just a 1. So a plus 0.35. And so we end up getting 0.35. And then what's this? 0.30. And now we have everything we need for our equilibrium expression. Products over reactants, right? So we write that the Kc is equal to 0.35 over 0.15 times 0.30 squared.
How come the 0.70 doesn't play into what the product's change is?
Say that again, Hannah.
So like how did you get to the product's change, the plus 0.35?
How did I get here?
Yeah.
Because we know that the change is 0.35, because we know that we went initially, and remember, this is all stoichiometrically related. So we went from 0.5 to 0.15. It decreased from a concentration of 0.5 to a concentration of 0.15. So we know that the difference was 0.35. And so that we know that that difference must be this gain.
And
So-
what about the H2? That just doesn't play into it?
So I see. Why isn't it this? Why isn't it the addition of this to equal this?
Yeah.
Okay, because we're just saying that that's the overall change of all the initial concentrations change by that much. That is the value for the change.
Oh, okay, got it.
So because this had a 2 here, it's going to be double that change. And this has a 1, so it's just still that change. It's a good question. I see what you're getting at. Why doesn't all of that change go there? Well, because that's just looking at the amount of change, not the total change, just the relative degree of change, if you will. So 0.35 divided by 0.15 times 0.30 to the second power because of this 2 coefficient. What do we get for that?
$25.9.
Thank you. All right, and that's our answer. Okay. All righty. Now, let's see, we have dihydrogen sulfide decomposing into hydrogen and sulfur gas. Okay. And they give us an equilibrium constant at 800 degrees Celsius. And then they say a 0.500 liter reaction vessel initially contains 0.0125 moles of dihydrogen sulfide, also at that same temperature. So find the equilibrium concentrations of H2 and S2. Okay, so again, this should hopefully be playing in your head, Vanilla Ice, Ice Ice Baby. And now you're ready to rock with some tunes to the backdrop, right? We're gonna do that. Maybe I'll just leave some brackets up so I don't have to write all that again. Well, we'll probably do something different now. Okay, so we got dihydrogen sulfide going to sulfur and hydrogen. And we got a 2 here. We must have a 2 here. We have to have a 2 there. No, I see. There we go. Okay. And they give us a KC. That's equal to 1.67 times 10 to the negative 7. And here in this case, the temperature doesn't matter. I mean, it matters, but we don't need to factor it in. All we know is that the temperature is staying the same, so we don't need to factor in temperature as a variable. And they say initially contains 0.0125, and it is a 0.5 liter vessel. So to get the concentration, we take 0.0125 divided by 0.5, which is essentially just kind of doubling it, right? So that is a 0.025. Okay, so you see where I got that? I just did a 0.0125 moles divided by 0.500 liters. And that gives us our concentration. our molarity. Okay. What's next?
The initial concentrations of the products are both 0, and then the change would be minus 2x plus x and plus 2x.
Good, because of the coefficient. Coefficient of 1, so 1x, 2x minus 2x, and so then we get a 0.025 minus 2x, a x, and a 2x. Now we put that into our equilibrium expression and set it equal to 1.67 times 10 to the negative 7, and we solve for x, right?
I had one quick question.
Yeah.
Would you account for the coefficient on the 2H2S initially there and multiply that 0.025 times 2? Or is that
No.
only accounted for change? No.
Yeah, we're saying that the initial concentration of this 2s is this. Good question.
Oh, okay. So that's
Yeah.
built in. Thank you.
Good question. Good question. Okay, so 1.67 times 10 to the negative 7 equals 2x times x over 0.025 minus 2x. And then put in our coefficients, right? So squared 2x squared. I think we're good. All right. So now what? What do we want to do?
Do we want to try a small x assumption for the bottom?
You betcha. So let's just assume, because I mean, 1.67 times 10 to the negative 7 is a small number. So I think it's a fair assumption to make. Yeah, I don't think it's even an iffy one. I think it's a good one. It doesn't mean we won't validate it, but let's just assume it. So now it's just 0.025 squared. And if combined all that, we end up with 4x. Let's just combine all of this. What is that? 4x cubed? Because 2x squared is 4x. 2x to the power of 2 is 4x squared times an x is an x cubed over 0.025 squared. And so that would be what?
Four x cubed over 6.25 times 10 to the negative 4th.
6.25 times 10 to the negative 4. Okay, now we want to get x by itself, right? So we multiply each side by 6.25 times 10 to the negative 4th. Right? That cancels this. Then we divide by 4. That cancels the 4. Then we take the cube root. That. And so what do you get when you take the cube root of 6.25 times 10 to the negative 4 times 1.67 times 10 to the negative 7 divided by 4?
I got 2.97 times 10 to the negative 4th.
I got 4.6 times 10 to the negative 4th.
Tiebreaker?
I also got 2.97 times 10 to the negative 4.
Okay. Let's go with 2.97 times 7 to the negative 4. Again, maybe just try 6.25 times 10 to the negative 4 times 1.67 times 10 to the negative 7. Divide that by 4, and then take the cube root, not the square root, of that answer. Okay, so we got another 2.9er. So let's just go with that. That equals x. So the next step is that we want to make sure that that was a valid assumption. So we take this and we divide it by what we were going to subtract it from. So 0.025. And then multiply it by 100%. Have a shadow. What do you guys get? Hopefully less than 5%.
One 1.2%.
1.2%. Great. That 1.17. Great. Wonderful, guys. So it's less than 5. That small x assumption was valid. So then we put in that number, that 2.97 times 10 to the negative 4, in for x. And what are they asking us for? Again, they ask us to solve for the equilibrium concentrations. Yeah, it's for H and S. So H is going to be 2 times it'll be 2 times 2.97 times 10 to the negative 4, and S is just going to be 2.97 times 10 to the negative 4. There we go. Those are our concentrations at equilibrium for sulfur and hydrogen. No quadratic equation required. But I can't guarantee that you won't have to use the quadratic equation on the final. I'm not going to say you do. I'm not going to say that you don't. So just be prepared to use that if you need to, okay? Ten. All right, now we're getting toward the very end of our stuff that we covered, right? So,
Sorry, can I clarify at the end of that one, don't we need to find the last concentration and plug that all into find the equilibrium concentration?
no, they give us, so they already gave
gotcha.
us,
Sorry, I was thinking the equilibrium constant. Okay, never mind.
yeah, they already gave us the Kc. And you don't even need to solve for H2S because they just say, what's the equilibrium concentrations of H2 and S2? Maybe if it would have said, what is the equilibrium concentrations for all three? Then you just do minus 2 times 2.97 times 10 to the negative 4.
Gotcha. Okay. Yeah, never mind.
And again, I know I say this a lot, but that's why I like to write, like take out all the numbers out of the word problem and put them on my piece of paper so that I know what I'm given. And that helps me kind of figure out the direction I need to know to get what they're asking for. Okay, we got to find the Bronsted-Lowry acid and base, the conjugate acid and base, and then write the equilibrium expression for Kc. Okay, so let's do that. And remember, water is an amphiprotic molecule, right? So it can be acid or base, depending on what it's being added to or what's being added to it. So this first one is H2SO4 and H2O going to HSO4 and H3O. So, any guesses on what is the acid on the reactant side?
H2SO4.
Yeah, it's sulfuric acid. It's a strong acid, as a matter of fact. So this is an acid. And if that's an acid, then water in this case is a base. All right. And so if this is the acid, this must be the conjugate base. And if water is the base, then H3O must be the conjugate acid. Okay. And then what do they want? They want the equilibrium expression. So that would be for H3O over H2SO4 and H2O. And again, we put the H2O in our equilibrium expression, but if we were going to use an ice table, we wouldn't concern ourselves with water for the ice table, okay?
For these acid-base equilibriums, are we ever going to have an exponent? Like, is there ever going to be an imbalance of moles where it's not just 1-to-1?
An imbalance of mole. You mean coefficients other than 1?
Yeah.
I don't think you will in this case, no.
Okay, cool.
Am I saying that that's impossible? Not necessarily, right? But with this, right, all you're doing is moving a hydrogen to some other molecule. And so usually you don't have to add coefficients because it's still balanced.
Wasn't there one problem that we were going over in our homework where we did have to multiply the hydronium concentration by 2 because of how it dissociated or something. I was just trying to
Well,
remember.
yeah, so
when that
if
applies.
you have, I believe it was calcium, it was a base, but yes, if you have calcium hydroxide, because you have essentially 2 hydroxide ions, once this dissociates into calcium, into hydroxide, because of that 2 there, then you would multiply it by 2.
Okay, so it's only like if it has the OH in parentheses that you would know that
Yeah.
it's dissociating to 2. Okay, sounds good. Thank you.
All good questions. What's this one? Okay. Now we have HCl3 and H2O going to H2CO3 and OH. All right. What's the acid? Which is the acid? Here, let me make my bigger. What's water in this case? Is it an acid or a base?
Acid.
Yes. So if that's the acid, and this is the base. And this is the conjugate base. And this is the conjugate acid. Okay, so if you're having trouble, one little trick is to say, well, what's happening to the water? If it's losing hydrogen, hydroxide is a base. That must be a base. So in this case, water is an acid. If the water on this side becomes H3O, now it's an acid. So water must be a base on the reactant side. Okay. And then the expression would be that. Okay. Okay, so there's one problem left. Let's take a break here since we got some time. Let's take a 9-minute break and come back at 2:20, and then we'll work on this last problem. And then if there's time after that, we can do the homework problem. Okay? All right. See you in a bit. All righty. Last problem. It went by quick. Should only give you guys an hour for the exam. What do you think? You up for it? No, it took us over an hour to do this practice test. I'm just joking. Bad joke. I'm sorry. This is my last opportunity to get some jokes in, so using it as best I can. Anyway, let's get back into it. This last problem, okay? This is like the apex problem. And I believe it was on one of the ICAs, maybe this last one, don't remember. But it's saying that aspirin, and those of you who take organic chemistry in the fall will probably, assuming that it's face-to-face, make aspirin. That is the quintessential organic chemistry lab. Of course, you won't make it to take it because that would just be dangerous. But it's a lot of fun. It's the one that everyone remembers. And anyway, it is a weak acid. It has a pKa of 3.5. And so they want us to calculate the pH of a solution in which one normal adult dose, and they give us, sorry, that's a 6.5 times 10 to the 2 milligrams, dissolved in 8.0 ounces of water. So we got to do some conversions and stuff like that, a nice table and solve for X and do all that fun stuff. Okay, so let's write down some stuff to help us on our way. First, what do they give us? pKa, 3.5. pH is what they want. And we have 6.5 times 10 to the 2 milligrams and 8 ounces of water. Okay. So let's I guess my first question is, did anybody do this? Did anybody get this done? Okay. See some head nodding. Good.
I did it on the ICA, and then I looked up the pH afterwards, which obviously doesn't account for the dilution, and then it just seemed way off. It seemed like way too strong, so I was trying to figure out what I did wrong.
Okay. Well, let's see if you end up with the same pH that we end up with today, and then go from there. Okay. So I think, the first one thing that we need to do is we need to get that milligrams per ounces into moles per liter, right? Off the bat. So, so let's convert what is 6.5 times 10 to the 2 milligrams. What is that in grams? Because we need to go from grams to moles to get our moles to liters, right? So what is 6.5 times 10 to the 2 milligrams in grams? Or 650 milligrams. Yes, 0.65 grams times 1 mole over, anybody look up the molecular weight of aspirin?
180.158.
180.158. And what do we get when we do that? Come on, brave souls. There's only 10 of you here, and that's me included. So don't be shy. We'll get through this together. 0.65 by 180.158, 0.0036.
I got the same thing.
All right. Moles. Okay, so that takes care of that. For water, we could say how many ounces are in a milliliter or a gram, because grams and milliliters are interchangeable because it's water. Density is 1.00. So 1 ounce equals how many mils?
I solved for it in liters, but I got 0.236 liters. So I guess that'd be 236 milliliters
0.236.
for liters. Yeah.
That's fine. You're just one step ahead. That's we can do that as well. If you can go from ounces to liters, that's fine too. Okay.
Yeah, I did ounces to quarts to liters just based on what I was seeing on our conversion sheet. Does that make sense?
That works. Yeah. Did you get this? Okay. So we all agree that 1 ounce is 0.236 liters. Okay. And we said there were 8 ounces. So that times 8.
Wait, sorry, I got 0.237 liters as what 8 ounces came
Oh.
out to.
Steven, is that what you got too?
Yeah, that was what I got. Sorry if I initially
All right.
did it wrong.
Okay.
That was my bad. Oh, 1 ounce. Oh, I'm so sorry. Yeah. Never mind then.
No worries. No need to be sorry. So, but essentially the process is you want to go from ounces to milliliters or to quarts to liters times 8. And there are different ways you can do that, right? But that's essentially how we got to this number. Okay. So then our concentration is now 0.0036 moles per 0.236 liters. Okay. And what is that? We divide this by this.
0.015 moles per liter.
0.015 moles per liter, or molarity. That's our concentration. All right. So we have our concentration.
Sorry, it's 0.015.
Oh, I'm sorry. Is that what you guys said? Or 0.15?
Yeah, 0.015.
Gotcha. Thank you, Hannah. Now we have our concentration. We also have pKa. So what can we do to get to our Ka? Well, remember, P is just a function, right? It's the log, negative log. And so if we have a pKa of 3.5, we can say that the Ka is 10 to the negative 3.5, right? So if our pKa equals 3.5, our Ka equals 10 to the negative 3.5. What's 10 to the negative 3.5?
3.16 times 10 to the negative 4th.
3.16 times 10 to the negative 4. So now we've gotten our information that was given to us in a convoluted sense, and we've manipulated it to get the right conditions that we can use to solve for pH right here. Okay. So I'm going to say that Ka equals 3.16 times 10 to the negative 4. And I'm going to erase all this other stuff. Because now we don't need that information. And now what do we do?
Ice table?
That's right. HA, H2O gives us what? If this is our acid, this is our base. So the conjugate acid is this. Conjugate base is this. Okay. And what? This is 0, 0. X, X, X. Some are going to be positive, some are going to be negative. Negative, positive, positive. And so we get a 0.015 minus X, X, and X. And so our expression is X squared over 0.015 minus X equals our Ka. Now, what do we do next?
Solve for X.
Solve for X, yes. Now, how do we solve for X, I guess, is the next question.
Should we try out this small x assumption?
Okay. Did you guys already do the small X assumption? I have.
I did one.
And was it, were you able to, did it work out?
Yeah, it did. I'm gonna double check right now, just because I ended up I ended up looking up a lot of the values
Okay.
for this because I thought we had to use the formula for aspirin. So
Chase said that it was too large.
Yeah, I really wanted it to work because I do not remember how to use the quadratic equation.
I
I know
just-
how to do it, so.
Okay.
too large.
So, yeah. So this Ka, I mean, that seems like a small number, but it, you know, it's not a really small number. I mean, it's smaller than 1, but it's large enough that, you know, we could do the small X, or it's small enough that we could do the small X assumption. However, when you solve for X and then divide it by this, it's not less than 5%. Okay. So rather than do that, I mean, you'll do that and then realize it's not. It's like 14%, like they said in the chat. So we're going to have to do the quadratic equation. Anybody remember the quadratic equation?
Is it a negative b plus or minus the square root of b squared minus 4ac all over 2a. Is that right?
Yes.
That's like 20 years ago.
What is it? Oh, there's a movie, You're My Boy Blue, with Will Ferrell in it.
I blacked out. I just blacked out.
Yeah, where he gets up and he's at the debate club and he just starts.
Yes.
What did I say? What did I say?
Yes, I just had that moment.
Not comparing you to Will Ferrell's character by any means, Miranda. So don't take it that direction. But yeah, that's what made me think of. Okay, great. So how do we put this into the quadratic formula? That's also part of it, right?
We have to get it arranged so it's like the squared x plus the x plus the number.
Yeah. So, so we can set it equal to our Ka, right? We have 3.16 times 10 to the negative 4 equals x squared over 0.015 minus x. Let me do this to get x by itself, right? So then we get 0.015 minus x times 3.16 times 10 to the negative 4 equals x squared. And we distribute. So 3.16 times 10 to the negative 4 times 0.015. What's that?
4.74 times 10 to the negative 6.
Okay. And then minus 3.16 times 10 to the negative 4x equals x squared. Did you guys get that so far? Okay. And then we set all that equal to 0. So 0 equals x squared plus 3.16 times 10 to the negative 4x minus 4.74 times 10 to the negative 6. Did I do that right?
Yes.
Okay. And then we plug in, right? This is A, B, C. So when you plug in B for the B's and the A for the A and the C's for the C's, what do you get next?
So would A be 1 or x squared? Like, do you include the x or just what's in front of the x?
Oh, just what's in front of it.
Okay.
Yeah.
And C keeps the negative sign.
Hmm.
And Dr. Franz, you said it is okay on the exam if we were to graph at this stage and then solve for the y.
Yeah.
Right? Okay.
Yeah,
sounds,
that's fine.
sounds good.
Yeah.
Okay, so when you solve the right side of it, then you get like the negative 3.16 times 10 to the negative 4 plus or minus. I got 0.002.
Okay.
Was that negative?
I think it's plus or minus 0.002 because you should come out with two different answers. One, well,
Yeah.
not necessarily positive, but two different answers.
Yeah. Depending on whether you're adding or subtracting those. Yeah. Okay, did anybody else get 0.002?
Yeah, I got a negative 1.
Okay.
0.00.
Yeah, that's-
Miranda, was that when you added or when you subtracted?
I haven't done the adding or subtracting yet. That 0.002 is just the right side of it. So like the negative
This part.
yeah.
Okay. And Jair has that as well. So they haven't gotten that far yet, Hannah.
So for adding and subtracting, I get a negative 0.002 and a positive 0.002.
Okay. Which one are we going to take?
Positive 1.
Positive one, right? Yeah, because what is X?
concentration.
Concentration. Can't have a negative concentration. So what were they asking for? They're asking for the pH. How do we find the pH if we have the concentration?
Take the negative log.
Yeah, right? Because pH equals the negative log of the concentration. Now, if it's a strong acid, you can take that, whatever that concentration is, and say that that's going to completely dissociate and going to be the same concentration of hydronium ions. And so we just take the pH. But since aspirin is a weak acid, we can't do that, right? We have to figure out the equilibrium concentration and then take the negative log of that. So when we take the negative log of 0.002, what do we get?
2.66. See, I got the same answer for x when I used small x versus when we just did this quadratic.
Oh, really?
Yeah, and that's what I was like. I used a solver too when I did the ICA because I was just like, it's close but not quite. But then the solver was giving me the same answer, so I'm like, I don't know why it's worth it to go through this whole quadratic equation when I'm getting the same answer. I don't know. That's just me being lazy and not wanting to do the math.
Yeah, that's okay. That's okay. Well, I can assure you that it's not always going to work out that way. And that sometimes if we have some values that are small enough, because like remember, so this right here is 0.002. And because B and C are, and A is 1, B is a smallish number, so it doesn't really change when you subtract or add, it doesn't really change things much, okay? Because B is so much smaller than this. And so sometimes, sometimes you get the right answer, you can't bank on that when making that small x assumption. It doesn't always work. In this case, I guess it did. Interesting. So I recommend that if it's less than 5%, don't further assume that you can assume that x is going to be the same. Just lucky, I guess, with this problem. Otherwise, I wouldn't make you do this because that's just an extra step.
Much appreciated. Thank you.
All right, guys. So that's the practice exam. As I said, final exam, it's going to be similar in format to that. So, practice this. You don't need to memorize the quadratic equation. You don't need to memorize the relationship of delta G of a reaction. You don't need to memorize any of that stuff. You just need to know, if I have a problem that looks like this, what do I use to solve it? Okay. And if you can pull out the right things, you should be able to figure it out, right? If it gives you KP and asks for KC or vice versa, then you're going to want to do that equation. Let me share my screen. Is this it? No. In this slide deck, you're going to want to use this equation here, right? If it's asking for a KP from a KC or vice versa. So really, your task is mainly to figure out which equation to use to solve for the problem. And I'm not saying that the problems are going to be exactly worded like the practice exam, only with different numbers. I mean, some might be, but if you can do everything on this exam, you'll be able to do everything on the final exam. All right. Okay.
Are we going to have like the 2-component pH problems? Because I was also a little confused on those from the ICA.
No, I think Chase, that's the one you wanted to go over. Is that correct? Yes. No, 2-component won't be on there. Titration, we did a titration problem the week before last, what was it, last Tuesday? That won't be on there. None of that stuff, okay? So I'll take any other questions, and if you guys don't have any questions, you're free to go. We have a little bit of time. We can go over question 10 on the ICA. And then if you have any further questions, send me a message or come see me tomorrow between 12 and 1. Okay.
For the day of the final, do we have like all day to do the final, but it's timed? Or do we have to take it during the lecture?
Nope. So just like with the midterm, you will have a certain window of time to take it, but you can start that window at any time of the day. So you don't have to be available between 1 and 3. If you'd rather take it before that or after that, that is perfectly fine.
And there's no lab or anything else, right?
No. Nope. You guys are, in fact, the week of finals, you don't have any lecture or any labs. This is just an optional review session that I don't have to do and you don't have to take. You don't have to be a part of. So this is everything this week is 2 hours. So it has to be started 2 hours before 3 p.m. No. So it's just got to be done. I'm going to say it's got to be done by midnight on Thursday. Okay. So if you want to take it if it's a 2-hour exam and you want to take it between 5 and 7, you can do that. Or between 8 and 10, you can do that. Or between 7 a.m. and 9 a.m., you can do that. Okay. So anytime that day. Yeah, so there's nothing else this week. It's meant for you guys to be able to concentrate on your exams, not be bogged down with other stuff.
Is it maybe going to cover more of the entropy stuff? I know we had the one Gibbs free energy problem, but I feel like there's a lot more entropy stuff that we went over. Is that a good idea to look?
We did some entropy stuff on the midterm, I believe. So really, it's just going to be free energy equilibrium, along the lines of that problem that is on the practice exam.
Great.
Mm-hmm. All right. Well, for those of you who I won't see again, it's been a real pleasure. Thank you for getting along through this class. And, I know it's less than ideal to do it online, but, I appreciate you guys making the time to attend lecture and labs and put in the work necessary. And again, for those of you who are taking Chem 103, I'll see you in a couple weeks. For those of you who have had enough chemistry for a while or a lifetime, maybe we'll cross paths again, maybe not. If we don't, best of, I don't want to say luck, best of fortune for you, okay? So you're free to go. If you want to hang around, we'll go over that problem on the ICA, and then we'll call it a day. Okay? All right. Let me see. Sorry, so which problem is it that you wanted to go over? Remind me again, the 2 component stuff? 7 on 10, okay. Okay, so. Let me find that ICA. Okay, determine the pH of each 2-component solution. We didn't go over 2-component solutions, right? So I don't expect this to be necessarily intuitive. I just threw it in there so you would have some exposure to it in case you go on in chemistry beyond LTCC. But essentially, if you have 2 strong acids and you put them together, then you are going to add those concentrations. If you have a strong acid and a weak acid, then you're going to just assume that the strong acid is going to suppress the dissociation of the weak acid. And, or that, you know, the level of dissociation is going to be minimal by comparison to the strong acid. So a strong acid and a weak acid, you're just going to look at the concentration of the strong acid. And then there'll be things, let's see what else is on here. So let's look at the first one. 0.0550 molar hydroiodic acid and 0.00850 molar hydrofluoric acid. Well, for that, we can say that hydroiodic is strong and hydrofluoric is weak. And so therefore, it's just going to be the strong acid that we take into consideration for the pH. So you just take the negative log of that 0.0550 molar concentration. And we completely ignore the hydrofluoric concentration. Now for B, what's happening there? It's got sodium chloride, 0.112, and then potassium fluoride, 0.0953. And this we have to do an ice table, okay? What's happening with this problem is that we're having an acid-base neutralization. And because sodium chloride is just a salt that we can say is neutral, the sodium chloride isn't really doing anything in this reaction, okay? It's just thrown in there as kind of a decoy, okay? But sodium chloride is neutral, so it's just going to be that potassium fluoride that's driving the pH, okay? And what we end up having is something like this. KOH plus hydrofluoric acid yields the potassium fluoride plus H2O. So that's where this potassium fluoride is coming from, right? Acid base, and then conjugate base, acid. Now, if we write that out, we can, as just for our ice table, we can say that we essentially have our F plus our water, and then we get our, what? Our HF and our base. I just inverted them to get our KF on this side. Okay. And this is a question, like we could put the K on there, but really what we're looking at is this as the conjugate base of this, right? It's not HKF, it's HF. So that's why we just write it as F minus as the conjugate. And then what did they give us as the concentration? So for salt, it's 0.112. And for KF, or in this case, just F minus, it's 0.0953, 0.0953. Okay. So the initial, water we don't worry about. Initial, minus X plus X plus X And we get 0.0953 minus x, x, x. Okay. Now, what didn't they give us? They didn't give us the KB. So this is one you just have to essentially look up. But they don't really have KB values. They usually have KA values. So if you look up the KA value for KF, let's see what that is. KA value. I'm getting a radio station. KFKA 98.7. I've got a 3.5 times 10 to the negative 4. Okay. KA equals 3.5 times 10 to the negative 4. All right. But now this is the conjugate base. We're using the initial concentration, not of the acid. This is the acid here. So it's the conjugate base. So we don't set it equal to Ka, we set it equal to Kb. And if you remember, Ka times Kb equals Kw, or 1.0 times 10 to the negative 14. So we could say that Kb equals 1.0 times 10 to the negative 14 over 3.5 times 10 to the negative 4. And what happens when you get that? (2.86 times 10 to the negative 11. Okay, 2.86 times 10 to the negative 11. Okay. So now that's our KB, and we set KB equal to our equilibrium expression, right? So let me erase this. And we say that this number down here is equal to x squared, right? Because x times x squared over 0.0953 minus x. Now, KB is a small number, right? To the negative 11. So let's assume that x is small, shall we? If we assume x is small, then it just becomes x squared over 0.0953. And so that's going to be 0.0953 times 2.86 times 10 to the negative 11 is equal to x squared, right? And then we just take the square root each side, and you get 1.65 times 10 to the negative 6. 1.65 times 10 to the negative 6. Great. One step ahead of me, so now I don't have to ask you. Okay, so if that's the case, we could divide it by 0.0953 and multiply it by 100% to make sure that that was less than 5%, that our X assumption is valid. Let's do that real quick.
I got 1.73 times 10 to the negative third percent.
All right, so it's valid, right? So now we can take this number and say that that's the concentration. And so that, because it's KB, that is going to be used to solve for our POH. Okay, so I'm going to erase this stuff here. We say that X equals 1.65 times 10 to the negative 6. POH equals a negative log of 1.65 times 10 to the negative 6. And what happens when you get that? .78. They're not asking for POH, they're asking for pH, right? So 14 minus 5.78 will give us our pH.
.822.
Okay. So it's a more challenging problem. And that's what these ICAs are always kind of designed to do, to challenge you guys, because it's got to, typically they're face-to-face and it's supposed to take 3 hours. And so by doing the ICAs and getting through those, it makes the problems that we do on homework and on midterms and stuff seem like a walk in the park. All right. What else do we got?
I think, at least for me, like the most confusing part was the setup of that. I was just trying to figure out, and I was like Googling what each of those was, just trying to figure out if they were strong or weak. And it was saying it was like a basic salt or something. And I was like,
Yeah.
Yeah, Chase said same for me. Yeah, I was like, have we learned about this?
No, you haven't. So we haven't learned about this. And yes, KF is a basic salt. It's the conjugate of HF in an acid-base neutralization, which you guys did cover acid-base neutralization in Chem 101, right? When you talked about like redox reactions, stuff like that, usually acid-base is covered. Yeah. So, you know, it's been a while. That was over 12 weeks ago, and a lot of chemistry in between. So, but you would have to know that KF is not an acid, and that the salt, the sodium chloride salt, is not an acid, but that the KF is a base. And so from that, you have HF. And that's where you would have to do your little digging and then be able to write that ice table from that. And you would have to know, of course, that the KF, because it's a base, means you have to use KB. And because you're not given Ka, you have to look it up and stuff. So it's like more independent work. So we did not cover this, and definitely challenging. And I'm glad you guys want me to go over this, because I don't expect you to know this. I do expect you to ask me if you don't know it, though. So, all right. So ammonium chloride and nitric acid. Well, this is a situation of a strong acid and a weak acid, okay? HNO3 is a strong acid, and so like A, it's going to suppress the ammonium chloride, and so we just take the log of 0.150. Okay. Piece of cake there. Okay, so the next one, same thing basically as what we did in B. So KBr, potassium bromide, is neutral. Sodium benzoate is going to be our conjugate base. And so we'll have essentially in the same like we did when we kicked off. So for B, when we kicked off the potassium, you can kick off that sodium when you write out your expression. And you can just write benzoate. Okay. So in same thing, benzoate plus water equals the conjugate acid of that, benzoic acid, and then the conjugate base. In this case, water's the acid, so it's going to be hydroxide. Right? So you can look up the formula for benzoate, or you can just write it. Benzoate plus water gives us benzoic acid plus OH, right? Benzoate is our base, so water must be our acid. Benzoic acid is the conjugate acid of this base, and OH is the conjugate base of water. In this case is the acid. And then they give us a concentration of 0.0887 in our ice baby. 0, 0, X, 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 right? You also need to look up the Ka for sodium benzoate. From that, solve for Kb by taking 1.0 times 10 to the negative 14 divided by the Ka for sodium benzoate. Then you set that Kb equal to x squared over 0.0887. That gives you your hydroxide concentration, right? Take the negative log of that to get your POH. Subtract from 14 to get your pH. So it's the same process as what we did in B. And I'll let you work that one out on your own. And I will extend the deadline for the ICA till tomorrow evening. And then the last one, HCl and HNO3. Two strong acids. So do you guys remember what I said about two strong acids? What do? You add them together. So it would be the negative log of, what is that? Let me get back to that. The negative log of 0.0450 plus 0.0225. Easy peasy on that one. Okay. All right. That's it. There won't be anything like this on the test. So Don't worry about that. Just get it done for the ICA purpose. But again, if you have any
Thank you for
questions,
going over that.
I'm sorry.
Thank
What
you.
was that?
That was good.
Oh, okay. Yeah, you're welcome. I will, again, be around for office hours tomorrow from 12 to 1 if you have any questions. If not, you guys will do fine. Just do this practice exam again. If you want, I'm going to post the recording as soon as I can. So if you want to watch this recording again, no, the exam's on Thursday. Thursday. Maybe I have it wrong in the syllabus. Hope I don't.
Well, I've got to run. Thank you so much. I will see you
Yeah.
either tomorrow.
Yeah, okay. Okay, Ali, we'll see you. Take care. Have a good spring break. No, so I'm looking here. It says 3:25. So 3:25 should be Thursday, right? Yeah, 3:25 is a Thursday. Okay, good. I'm glad we cleared that up because it won't be available on Friday. Thanks for all your participation. And oh wait. Okay, you're still confused. So just hold on. So on the syllabus, it says 3:25. So March 25th. Yeah, so right here, final exam, Thursday, March 25th. Oh, okay. Okay, good. All right. Jer, thank you for all your participation in class. I really appreciate it. You know, going through the problems with us and doing the answers with us. You know, it's much appreciated. You too, Chase. I really value your guys' help with this. And I think it's better for you guys to go through these problems as we go through them. And I know that you both always do. So thank you for that. And if you want to see me tomorrow between noon and 1, great. If not, just like I said, go over this exam, this practice exam until it seems natural, and then you'll be just fine. Okay? All right. Thanks, guys. I'll see you around.